The next thing I want to talk about is something called the divergence theorem. And so what our divergence theorem says is that the total outward flux of a vector field A through some closed surface S is the same as the volume integral of the divergence of A. So let's put that into equation form. So we're saying that the surface integral over some closed surface of A, so as we've seen in a previous video, we can evaluate that as the integral over the surface A dot ds. We're saying that by the divergence theorem, this is equal to the volume integral of the divergence of A. So del dot A, and then differential volume. And so a couple conditions, of course, we need our values that are being integrated to being continuous, but other than that, this is going to apply to any volume bounded by a closed surface. So applies to any volume, V, bound by closed surface S. And of course it needs to be a closed surface because we're talking about outward flux. We can't have outward flux if we have, for instance, just a two-dimensional sheet. So by closed surface S. But as I said, our integrands have to be continuous in that region. So provided that both A and our divergence of A, so del dot A, are continuous in our region of interest. So both of those items have to be continuous. And so what we're going to see later on is that typically the right side of this equation, the volume integral, is going to be a lot easier to evaluate than doing our surface integrals. And so this is going to come up a lot later on as we're deriving equations or as we're solving example problems. So this is definitely something good to either memorize or have handy, ready to reference quickly as we're sort of doing some of these things later on.